Hi everyone, in this chapter section, we are going to relate the electrical potential, free energy, and equilibrium together. From chapter 17, we learned that the spontaneity of the process can be determined from the change of entropy of the universe, right? And for the spontaneous process, the entropy change of the universe have to be positive. And we also related that to the gift free energy of the system as well, or of the reaction. And for a spontaneous process, the change of the gift free energy of the system have to be a negative value. And later on, we related this spontaneity with the equilibrium, and we looking at how the delta G, right, is related to the K value, right? For example, if the reaction is spontaneous, we know that the reaction is going to be favoring the forward direction. Therefore, the K value that as written in the forward direction would be a large value, indicating that at the equilibrium, the product is abundant, right, compared to the reactant. Therefore, in this case, when we talk about the spontaneity, we also looking at how we can predict spontaneity in the redox reaction as well, and we use the cell potential, right, to in order to tell us whether the redox reaction is favorable or unfavorable in the forward direction, right? And then we learn that in for the reaction to be spontaneous, the sign of the cell potential have to be positive. Therefore, in this case, all of these are related, all of these spontaneity terms are related with the equilibrium. So in this chapter, that's what we're going to focus on. You can read the detail of this chapter section from the OER textbook, chapter 18.6. Shown here is the equation that relates between the standard gift free energy of the reaction and the standard cell potential for the redox reaction. Note that the E0 reaction is identical to the E0 cell. The reaction is generally used for any redox reaction, and cell is specifically for the electrochemical cells, okay, that are either galvanic or electrolytic cells. The N is the number of electron transfer between oxidation and reduction half reactions. F is a Faraday constant, which given here. And you can find out the standard reaction potential by using the standard reduction potential that we learned earlier, which is the standard reaction potential would come equal to the difference between the standard reduction potential of the cathode minus the standard reduction potential of the anode. Again, because if we are talking about the general redox reaction, we don't have to determine cathode and anode because those are the electrode, which is part of the electrochemical cell. We can literally just replace this with the standard reduction potential that belong to the reduction half reaction, and the anode would be the standard reduction potential that belong to the oxidation half reaction. Okay, so that's what it is. And once you are able to relate the standard reaction potential to the standard gift free energy change, then you can plug it into the equation that we learned from the chapter 17 that related the standard gift free energy change with the equilibrium constant for the reaction. Okay, so therefore all of these are related. Now let's take a look at example on the next page. This example will allow you to practice more of how to balance the redox reaction by using the half reactions method. And also we are going to use this balanced redox reaction and looking at the half reactions in order to determine the number of electron transfer and determine the standard reaction potential for this redox reaction, and eventually we are going to obtain the change of the gift free energy of the reaction and also equilibrium constant as well. Okay, so let's take a look at example 1. Before we start with writing the half reactions, first we will need to determine which species loses electron and which species gains electron. So I'm going to go ahead start with manganese oxide ions. Okay, so oxygen would be -2 oxidation number. There are 4 of them, so total would be -8. But in this case, the overall charge is -1. In order to solve for the oxidation number of manganese, it would be manganese plus 4 oxygen times -2 for each oxidation number of oxygen, right? Set this equal to -1 because the overall these ions is having the charge of -1. So for this, you are going to obtain the oxidation number of manganese to be +7. Okay. Do the same thing for water as well. -2 for oxygen, +1 for hydrogen. Lead free element would be 0. Lead 2 plus, it would be the oxidation number would be the same as a charge. Manganese oxide, oxygen would be -2. There are 2 of them. So in order to make this to be neutral, right, because the overall is a neutral molecule, you can set up the equation as well, which is the manganese oxidation number that we don't know plus 2 oxygen, and each of them has -2 oxidation number. Set this equal to 0. You can solve for this and you are going to obtain oxidation number of manganese equal to +4. Okay, so do the same thing for hydroxide ion. So aside oxygen first, -2, and hydrogen is +1. Overall would equal to -1, which is the same as the charge of hydroxide ions. In this case, if you look at the element that undergoes oxidation change, that would be the one that undergo redox reaction, right? Or having the electron transfer involved. Okay, so let's take a look at manganese here. Manganese going from manganese 7 plus to manganese 4 plus is indicate that manganese is gaining electron. Therefore, in this case, manganese undergo reduction. Okay, and what else? Looking at other element. Another element that you see that changing oxidation number is lead, right? Lead going from lead 0 to lead 2 plus. This lead undergo oxidation. Okay, so now we know which one is undergo reduction or oxidation. The next part that we are going to do is we are going to separate them into half reactions. Okay, so I'm going to start with the reduction first, which is the manganese oxide. Okay, so what I'm going to start with, I'm going to ignore water and hydroxide ions for now because those, according to the method of balancing equation, will come play a role when we actually add the number of elements to be equal. So in this case, I'm just going to start with manganese. Okay, so I'm going to start with manganese oxide 4 plus. Okay, oh sorry, minus manganese, or I have that incorrectly. So let's do MnO4 minus. Okay, and I'm going to pair this up with its conjugate pair, and that is the MnO2, right? I will not care about those elements that do not change oxidation number. All I do is that I need to just find out the conjugate pair for this. Same thing for oxidation half reaction as well. Okay, so if you write this, you are going to get lead, right? So that's between lead and lead 2 plus, right? Because these two are the conjugate pair. Okay. And the next thing that we will need to look at, let's go ahead to look at the reduction half reaction first. So for the reduction half reaction, first you will need to balance the number of element. In this case, you see that the number of element manganese are equal on both sides, but oxygen on this side has 4, this one has 2. In order to balance the number of oxygen, you will need to add water to make the number of oxygen equal. Therefore, you can add 2 water on this side in order to make the overall number of oxygen to be 4, right? So 2 from here and then 2 from here. Total would be 4, which is going to equal to this. Okay. However, when you add water, you are adding hydrogen, 4 of them. In order to make the number of hydrogen on this side to be equal on this side, you are going to need to add the proton. Okay, so you need to add proton, which is going to be 4 of them. Okay, now if you check, you will see that manganese equal, number of oxygen are equal, number of hydrogen are equal, so that's good. The next thing that we will need to look at is the example 1 has the hydroxide ions, which is the identity of the base. Therefore, in this case, we will need to make sure that we balance this equation in the basic solution. Okay, in order to make this balancing equation to be in basic solution, what you need to do is you will need to add the hydroxide ion on both sides of equation. Okay, so in this case, we can add hydroxide. And how do you know how many hydroxides? Well, you need to base off the number of protons that are available. Okay, so again, the proton is in the identity of the acid. In order to neutralize this, you need to add the same amount of the hydroxide ions. Note that all of these elements already balanced. Therefore, if you are adding hydroxide ions here, you also need to do the same thing on the other side too in order to balance each other out. Okay, so in this case, I'm going to go ahead add 4 hydroxide, okay, on both sides of equation. The reason for that is because, again, you will need to make sure that the hydroxide and proton are cancel each other out. And these 4 proton add to 4 hydroxide, they are going to neutralize each other to become 4 water. Okay. Therefore, in this case, if you look at it, the product of these reduction half reaction would be manganese oxide ions, right? Plus 4 water, but wait a second, these 4 water on the reactant side, the water is also present on the product side as well. Therefore, these two can also cancel each other out. So if you cancel these two from each other, okay, you are going to get the total of 2 water on this side. Okay, so that means in this case, the overall reduction half reaction would be plus 2 water, and it's going to become manganese oxide plus 4 OH minus. Okay, make sure that you have the number of elements equal again. So 1 manganese, that's good. 4 oxygen plus 2, that's 6. Okay, so 4 oxygen plus 2, that's 6, that's good. 4 hydrogen, this is also has 4 hydrogen, that's good. Therefore, in this case, this reduction half reaction has the same number of elements on both sides of equation. The next step that you will need to look at is the charge, okay, the summation of charge. Okay, so in this case, I'm going to go ahead, add the charge together. So the charge on this side, total would be -1. The reason for that is because you have -1 from magnesium oxide ions, right, and 0 from water. And in this case, you will see that you have total of -4 because you have 4 hydroxide ions. Okay, so that means in this case, the charge are not balanced. Therefore, this reduction half reaction is not balanced yet because the amount of charge have to be equal on both sides of the equation. In this case, in order to make these two to be the same, you will need to add the electron. In order to balance the charge, you will need to add electron. Therefore, going from -1 to -4, you will need 3 electrons added to the reduction half reaction. Okay, so therefore, in this case, we have -1 and we have -3 from the electron. Total of this charge would be -4, which is equal to the other side of reaction. Therefore, in this case, these represent, so I'm going to eliminate the summation of charge real quick so that way I have more space here. Okay, so therefore, in this case, this is the balanced reduction half reaction. Okay, so that's already balanced reduction half reaction. Next, let's take a look at lead to lead 2 plus. Okay, so again, going from balancing the number of elements first before you balance the charge. Okay, so balancing the number of elements is going from lead to lead 2 plus. There are 1 lead on each side, that's good. Next, we are going to look at the charge, right? It's going from lead 0 to lead 2 plus. In order to make the charge equal, you will need to add 2 electron on the other side to make this overall charge to be 0, which is going to equal to that. Okay. Now, before we write the balance equation, you first make sure that the number of electrons are equal first. And since these two are not equal, so you will need to make it equal. So you will need to multiply the whole thing by 2, right? For the reduction half reaction, and for the oxidation half reaction, you are going to multiply the whole thing by 3 to make the number of electrons equal to 6. Okay. If you do that, you are going to obtain the number of coefficient for the manganese oxide to be 2, okay, and for water would be 4, for lead would be 3, lead 2 plus would be 3, manganese 2 would be 2, right? Because you are multiplied this one to here, therefore it would be 2. And then hydroxide, since we have 4, 4 multiplied by 2, that would be 8. Okay, so I'm going to write 8 here. Okay, so again, and we will not see number of electron anymore because electron would then cancel each other out, right? Because they are on the opposite side of equation. And in this case, the number of electron that transfer would equal to 6 electron. Next, we will need to determine the standard reduction potential for these two half reaction. Okay, so we are going to go back to page 114 of this lecture manual, which is belong to part of the 18.3 chapter section. If you go to chapter 18.3 chapter section, page 114, you will see the list of the standard reduction potential. Okay, so in this case, the standard reduction potential, it doesn't affect by the number of electron that transfer. Therefore, whatever that is involved here, the number will not change as you change the number of electron. So if you're looking at the reduction half reaction, what you can see is that it's involved with manganese oxide permanganate ions, right? And then water, manganese oxide, and 4 hydroxide ions. If you're looking at the list of these, this is belong to reduction half reaction. This is also reduction half reaction. That's perfect because it's gonna be written identical. Okay. So we are looking for MnO4 minus. Okay, so we see one here. Okay, so I'm going to underline. So we see one here, MnO4 minus. And there are another species right here is also Mn4 minus as well. So which one should we use then? This is when you will need to look at the rest of the reduction half reaction. The equation that we are interested in, the pair of the conjugate pair is the permanganate with the manganese oxide. Okay, so the first one is the permanganate, but there is no manganese oxide. Therefore, this is not the one that we want. Okay. The second one is the MnO4 minus and MnO2, which is identical to what we are looking for here. Okay, so therefore we are going to focus on this one right here. Okay, the value of the standard reduction potential here would be exactly what is written, right? So we will not change anything. Even though the number of electrons change, we don't have to change it because the standard reduction potential doesn't it is independent from the number of electrons. So this would be 0.59 volt. Okay. You will need to do the same thing with lead as well. Okay, so we will need to find out lead and lead 2 plus. Okay, so the pair would be lead and lead 2 plus, but this is the oxidation half reaction, but this list here is the known value of the standard reduction potential that represented by the reduction half reaction. Therefore, in this case, you will not see this reaction written on here, but it's going to be the reverse process of it because this is the oxidation. The reverse process would be the reduction. Therefore, you are going to looking for lead 2 plus 2 electron that become lead, right? So in this case would be lead 2 plus 2 electron become lead. So we are going to use this reduction half reaction, okay, because it belongs to lead. And again, the value that is indicate here is the value of the standard reduction potential, which is this value right here. Okay, so it's the reduction potential. This is also the value of the standard reduction potential. Therefore, you do not have to change the sign of the value. It's going to still become a negative 0.13 volt. Okay, so again, the reason why I don't change the sign because the value is indicated for the standard reduction potential, and this is the standard reduction potential. But the equation that written, this standard reduction potential is belong to the reaction half reaction, which is written as this. But our half reaction is specified as oxidation half reaction. Therefore, you will need to flip this, right? So, but again, the reason why we don't need to flip this because the formula that we are going to use is require the standard reduction potential value. So therefore, we don't need to change the sign of it. We're going to read as it is and report the value as it is. Okay. So to calculate for the standard reaction potential, we are going to use the standard reduction potential that belong to the reduction half reaction or the cathode, right? Minus the standard reduction potential that belong to the oxidation half reaction or the anode. Okay, so again, the reason why I'm not changing the sign of this because it's the formula is require the standard reduction potential. Okay, so that's why I don't flip the sign. Pretty much the negative in front of this is actually already account for that switching the sign. Okay, so we don't have to worry about that. So let me erase that for a second. Okay, so I'm going to go ahead put in the number of the standard reduction potential that belong to the reduction half reaction, which is 0.59 minus the standard reduction potential that belong to this oxidation, which is negative 0.13. Okay, the total would come out to be positive 0.72 volt. Okay, so positive value indicate that this reaction is spontaneous. Okay, so therefore, in this case, if you go back to, if you keep going up to the question below, is this reaction spontaneous or non-spontaneous in the forward direction? The answer would be this reaction is spontaneous in the forward direction because the standard reduction potential is positive. Okay, you can actually determine this by looking at the sign of the delta G as well. In order to calculate the sign of the delta G, you are going to use the formula that we see in the previous page, which is equal to negative NF E naught reaction. Okay, so N is the number of electron transfer. In this case, it would be 6. Okay, F is the Faraday constant. The value is 96485 joule per mole per volt. Okay, and E standard reaction potential that we just calculate is 0.72 volt. So calculate this out. You are going to get the unit in joule per mole for the unit of the delta G. And the value for delta G will come out equal to negative 4.168 times 10 to the 5th joule per mole. Note that I'm not going to round the value of delta G yet. I'm just going to underline. From the previous calculation, there are two significant figures from the standard reaction potential. Therefore, the final answer for delta G should have two significant figures. But I'm not going to round yet because we are going to use this delta G in the calculation of the equilibrium constant K. So I'm just going to underline to indicate that that should be only two significant figures. Okay, so for K, in order to find K would equal to, from the chapter 17.2, if you want to review that, 17.3, the equation for K that related to delta G, it would be E raised to negative delta G over RT. Okay, so therefore you are going to do the exponent of negative delta G, which is negative 4.168 times 10 to the 5th joule per mole. Okay, and divide this by the value of R, which is a gas constant, universal gas constant, with the unit in joule per mole per Kelvin. The value for that would be 8.314 joule per mole per Kelvin. Okay, and then multiply by the temperature in Kelvin. Temperature is indicated is at 25 degrees Celsius, so that would be 298 Kelvin. Okay, if you cancel the unit, you are going to see that the K will have no unit. Therefore, in this case, the value of K would equal to E raised to 168.2. And if you do this, you are going to get the value of 1.15 times 10 to 73. Okay, so that would be the value of K. And because the calculation from the previous step has two sig fig, therefore this step would also have two significant figures as well. So here are the answer for the E reaction. Okay, and this is the answer for delta G. Okay, and then last one is the answer for K. Okay, if you look at all of these, you will see that they all would predict the same thing. They all indicate that this reaction is spontaneous in the forward direction because the standard reaction potential come out to be a positive value, delta G come out to be a negative value, and you are going to have the amount of the product to be predominant at equilibrium, because the reaction is most likely to go completely forward, right? Because it prefers spontaneous in the forward direction. Therefore, in this case, we can say that the reaction is spontaneous. Okay. Because the E reaction is positive, right? Delta G of the reaction is negative, and the K equilibrium is greater than 1, right? Because it's a high value indicating that it's produce more of the product at equilibrium. So we can say that at equilibrium the product, okay, predominant, because you have a large value of equilibrium constant. Okay, so that's what it is. Now let's take a look at example 2. I would like you to use example 2 as the practice. So let's go ahead, pause this video and complete example 2. When you finish it, then you can resume the video to check your answer. For example 2, again, this reaction is not balanced yet, right? So it's require you to input a coefficient in front of each of those. So first, you will need to determine the oxidation number for each of those. So free element would be 0. Okay, hydrogen plus 1 would be plus 1. Silver would be plus 1. Water assign oxygen first, followed by hydrogen. Okay, so therefore, you will see that going from silver to silver 1 plus, silver loses electron. Therefore, silver is undergo oxidation half reaction. Okay, and for oxygen, is going from oxygen 0 to oxygen 2 minus, oxygen receiving electron. That's why it's become more negative. Therefore, this is the reduction half reaction. When you are able to determine which one is undergo which type of half reaction, then you can split out the half reaction. Okay, so I'm going to start with the reduction half reaction. Again, in this case, we are going to look at only the conjugate pair. The conjugate pair for the reduction half reaction is O2 that go to H2O. Okay, so that's what I'm going to focus on. And the other pair that we see from the oxidation half reaction is silver, that is go to silver plus. Okay, so I'm just going to start from here. Again, do not worry about proton or water yet, because eventually that's going to come play a role after you finish balancing the half reaction. Okay, so let's go ahead looking at the reduction half reaction first. Going from oxygen to water, you see that this reaction is not balanced yet. You will need to make the number of number of oxygen to have to be equal first, right? By adding water if it's not equal, and then once the number of oxygen equal, then you can go forward to do hydrogen, right? So in this case, in order to balance out, in order to make the number of oxygen equal, you will need 2 water, right? In order to make the number of oxygen equal to 2, okay? Because you have 2 water on the product side, therefore you will need to add proton in order to make the number of proton equal. Okay, so how many proton? Since there are 4 hydrogen on the other side, this one have to have 4 proton on this side. Okay, so therefore, if you check the number of elements, you are going to see that you have 2 oxygen, 4 hydrogen, and 4 hydrogen. So perfect, the number of elements is already balanced. The next thing you need to check is the charge. Okay, the charge on this side is 4 plus, this one is 0. In order to balance the charge, you will need to add electron. Okay, so how many electron then? Well, because this one is 0, right? This one is 4 plus. In order to make this to be neutral, you will need to add 4 electron to neutralize the positive proton. Okay, so we need to add 4 electron. So now this reaction, half reaction is already balanced, right? Because the number of elements are balanced and the charge also balanced as well. Okay, so when you finish, move on to the next. The next one is oxidation half reaction. If you're looking at this, you will see that silver go to silver plus is indicate that silver loses electron. So losing electron would be on the product side, and that will be just one of them because lose 1 electron to become 1 positive charge. And as you see, in order to combine these to get the overall reaction, you need the number of electrons to be equal. Therefore, you need to multiply this oxidation half reaction by 4. Okay, in order to make the number of electrons equal. Once the number of electrons equal, then you can combine the reduction and oxidation half reaction. Therefore, the overall reaction for this case, you are going to get 4 silver plus oxygen plus 4 proton. Okay, and then electron would cancel out, so we will skip to the product part. Plus silver plus 4 of them, because we need to multiply this by 4, right? And then plus 2 H2O. Okay, so if you're not sure whether this is a correct overall balanced product reaction or not, you can check first number of element. 4 silver, that's good. 2 oxygen, that's good. 4 proton, 4 hydrogen, that's good. Okay, then you can look at the summation of the charge on both sides. So we have 4 plus here, we also have 4 plus here. Therefore, this would be the correct balance redox reaction. Okay, so you can now write out this balance equation coefficient in front of each of these, right? So 4, 1, 4, 4, 2. Okay. And next, to determine the standard reduction potential for each of these half reactions, you will need to go to section 18.3 to obtain the value from the table, right, for the standard reduction potential. So again, the value of this will not be affected by the number of electron. Okay, so therefore, in this case, if you're looking at reduction half reaction that involve with oxygen 4 proton, the only thing that involved with that is oxygen that become water, it would be this one right here. Okay, so therefore, the standard reduction potential for this reduction half reaction would equal to 1.23. Okay, so it's come from this guy right here. Okay, and another one is the silver to silver ions, this one. Okay, so if you're looking at it, this one would be similar to this. Okay, so except this one is oxidation half reaction, but this one is reduction half reaction. But the number that we want to read is for the standard reduction potential. Therefore, this value would be as is written from the table. Okay, which is 0.80 volt. Okay, because it belongs to standard reduction potential. Okay, so when you finish this, then we can move on to the next step. All right, next step, asking for the number of electrons that transfer. So in this case, total would be 4 electrons that transfer. And the standard reaction potential would come from the standard reduction potential that belong to the cathode. Okay, minus the standard reduction potential that belong to anode. Okay, so therefore in this case, it's going to be 1.23 minus 0.80. The answer would equal to 0.43 volt. Okay, so after you obtain the standard reaction potential, then move on to the gift free energy, which is equal to negative NF E reaction. Okay, so the number of electron is 4. Faraday constant is 96485 joule per mole per volt. You do not need to memorize the Faraday constant. It will be provided on the exam. And the standard reaction potential that we just calculate would be 0.43 volt. This answer should come out with 2 significant figures and with the unit of joule per mole. And the answer is negative 1.66 times 10 to the 5th joule per mole. Okay, so again, I'm not going to round it yet, so I'm just going to underline this. It should be 2 sig. Okay, now K, the chemical, the formula for K related to G would be E raised to negative delta G naught over RT. So plug in the value, negative, and then delta G would be a negative value, also 1.66 times 10 to the 5th joule per mole. Divide by the gas constant 8.314 joule per mole per Kelvin, and then temperature at 298 Kelvin because specified 25 degrees Celsius, then you will get E raised to 67. Okay, so the answer will equal to 1.25 times 10 to the 29th. And again, from the previous step, there are two significant figures, so this one would have two significant figures as well. Therefore, the answer for E reaction would be 0.43 volt, and the delta T would be a negative value in joule per mole, and equilibrium constant would have no unit. Okay, so therefore, this reaction would be spontaneous. Okay, because again, the standard reaction potential is positive. Okay, delta G of the reaction is negative, and you are end up with a large value of K EQ. Okay, so indicate that the product is predominant, right, at equilibrium. So at equilibrium, the product, okay, predominant because this reaction is spontaneous in the forward direction, or the value of KEQ is large.